Alright, so we're jumping ahead to section 7.2, and here has nothing to do with matrices. We're done with that for a while. Now we're starting to talk about sort of counting and probability, but we're going to start with talking about our sets, which are going to be the basic sorts of things that we are counting and the way that we describe uh, events and probability. Now, what is a set? Well, here's a sort of a definition. A set is a collection of objects, which are called members or elements. Okay, great. So, some examples. We have the set of whole numbers. That's a set. We have a set of people in our class. That's a set. Uh, uh, just anything you can think of. There's the set of, your dog, the letter 3, and the concept of, you know, special relativity. Whatever. That's just a silly set that has 3 weird things in it. Your dog, the letter 3, and the concept of special relativity. Whatever. But generally, I'm just going to get rid of that because generally we're going to be thinking of sets as things that sort of go together in some sort of nice sense. So how do we denote sets? We denote sets by capital letters. A, B, C, D, etc. I don't need to tell you what the capital letters are. Great. Now, if I have a set, if I have a set A and an element X, I write X is an element of A, or X is in A by the brief mathematical symbology. I write X, then I write this little symbol right here. It's sort of the Greek letter epsilon, but it's sort of stylized. Then I write A. So that's what this means. X is an element of A. X is in the set A. However, you might have an element which is in some set, but it's not in A. So I also write X is not an element of A, or X is not in A, by writing the same sort of thing, but I put a slash through this epsilon. So that means X is not an element of A. Great. And finally, there's one sort of special set called the empty set. So the empty set is the set that has no elements in it. And we denote it by this sort of symbol right here. This is similar to the Greek letter phi, but really think of it like a 0 with a slash through it. Okay, great. So how do we talk about sets? How do we actually describe sets? Because, I had some ways up here. Hold on for a second. Whoa. I just, sort of wrote out some descriptions of sets, but we're going to want better ways to be able to write down what exactly a set is. And we have 2 major ways of doing this. Now, the book calls the first way here the listing method, but I prefer to call it the roster method, so I might say that. What exactly is the listing method or the roster method? We just list out all of the elements of the set between curly brackets, these being curly brackets right here. Okay. Why is it called the roster method? Well, calling it the roster method makes sense because it's like saying, okay, what is the set of all students in my class is equal to my roster. I have a roster, which literally is a list of all the students in my class. So that is a way of describing the set of students in my class. So that's why we like to use the term roster method. Anyways, so here are some examples of using the roster method, or the listing method. So for example, the vowels, we can write them as A, E, I, O, U, Y. We better include Y because otherwise my last name, Breik, does not have a vowel in it, and I don't know, when I say it there is a vowel in it, so Y had better be a vowel. Okay, but see, I just list them out. Great. How about the digits? No, not, hey, what are your digits, but just literally the digits that make up all of the numbers. All numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's funny. This font I use puts a little dot in the 0. It's like two eyes looking at you. Okay. Digits. Great. Just list them out. But sometimes when we want to write down yes, a set using the roster method, we can't write out all the elements. For example, the counting numbers, which are 0, 1, 2, 3. I can't finish writing all of the counting numbers that there are because, well, there are infinitely many. You think of, you count up to 1,000,000, I'll count up to 1,000,001. I can always count up to one number higher than whatever you can count up to. So, well, whatever. Too bad. So these dots here, which you might know as ellipses, I guess this is an ellipsis, indicates that the pattern that's established by the first few elements in the list continues. So we can just assume that when I write 0, 1, 2, 3, 4, 3, etc., then this is really 0, 1, 2, 3, 4, 5, 6. I'm going to stop. I messed that up anyways. And finally, we could write the empty set as this set right here. There's nothing in there. There's nothing in here. I didn't put anything in here. There's nothing in here, so the empty set is the set with no elements. Now let me just quickly do some examples of then using the inclusion notation. So we have that the vowel, the letter A, is indeed an element of the set of vowels. How do I know? I can just say, well, is A in here? Yes, there it is. It's sitting there. Whereas, say, the letter T is not in the set of vowels because, well, I just looked down the roster. Is it there? No. Here, yes, it's listed out. Here, no, it's not listed out. Or, say, the number 100 is in the set of counting numbers because it follows the established pattern. Whereas the number, 1 point whatever, whoa, oops, oh man, oh come on, what are you doing? Thing, stupid handy buttons that are supposed to help me out. Anyways, this number is not in here because it does not follow the established pattern. Because all these numbers are whole numbers right here, and this is some decimals, so it's not going to be in there. Now this is not necessary. Oh, and finally one thing. When using the roster method, we do not repeat elements, and the order doesn't matter. So that means things like this doesn't really make sense. I might as well just write it like this. I could write you down on my roster for my class 5 times. You could register for my class 5 times, but you're still only coming to it once, and you'll still only get credit for it once. You probably don't want to have your financial aid or yourself pay for it 5 times, but writing it out more than once doesn't really change the fact that no, all we care about is it in here or is it not in here? writing it out 3 times is redundant. Also, if I wrote 1, 2, 3, that's exactly the same thing as 3, 2, 1. I don't care about the order that I write things down in. All I care about is what is inside of the set. Okay, so the roster method is only so good at describing things. Sometimes a better way of describing a set is via some sort of condition. Now this is the rule method, although I like to call it set builder notation. And it basically works like this. You write a bracket, and then you write down, say, x, or the general sort of elements that you're looking at. Then you write a bar. Then you write some sort of property that x satisfies. And then you draw a bracket. So what this means is the set of all x such that x satisfies this property, whatever that might be. Mathematicians like to say that this line means such that, whatever. Great. What they do. But let's look at some examples of this using set builder notation. So for example, I could say that the even numbers are all the whole numbers x such that x, all whole numbers, x such that x is a whole number divisible by 2. I could also say that the even numbers are all the numbers 2 times x, where x is a whole number. Those are 2 ways of describing it. Here I'm saying that I'm looking for everybody who's an x, which is a whole number divisible by 2. And here I'm saying, well, let's start with all whole numbers, and then I'm just looking for the multiples of 2. Okay. The digits I could write out maybe more simply as x, where x is a whole number, and x is between 0 and 9. And say the points on the line ax plus by equal to c, I could write this as the set of x comma y pairs xy such that ax plus by is equal to c. So that's sort of let me just put this onto one line here. That's a nice way of writing down, this is really the graph or the set of points on a given line. Okay. We can also write the empty set out in terms of set builder notation. A way to write it out is to write x and then write some sort of condition that is clearly never true. So for example, let's look at the set of all x such that x is a Major League Baseball team I've pitched for. I don't know if you watch baseball, but if you do, you've never seen me pitch for a Major League Baseball team. And that's because my talent is too great for them to comprehend. So no, it's because I can't throw for crap. Great. Finally, let's just note sort of a basic distinction of sets. We have finite sets versus infinite sets. And finite sets are ones you can count out. Ones that you can actually count all the number of elements, and infinite ones you can't count out because you never stop never stop counting. Just goes on forever and ever and ever and ever and ever. So, examples of finite sets were the digits, the vowels. What else did I talk about? Digits, vowels, whatever. But infinite included things like the counting numbers, the even numbers, the points on a line. We've even talked about, about this in the context of solving linear equations. So, we've already talked about finite and infinite. So, great. Gotta stop. 15 minutes.